these address the questions we're interested in. And then the second question is, what additions to our modeling tools are needed and what additional processes are important to add to our existing modeling tools and why? So maybe as a quick survey, how many, I mean, I look around, it seems like most people here are on the measurement side versus the modeling
That's
side.
why I was trying to get Da Chang to come up here, because he's doing a model of regolith formation.
So that's sort of the first, so maybe that is need in terms of bringing expertise or, someone or effort to build that side of our modeling. Right?
Well, what would you want to model?
I don't know. Well, we can talk about that, but I guess just in terms as a first cut here, just in how we split our groups up. So I guess I'll just maybe open it up to a survey of how we're doing in terms of measurements that we're making, and are there glaring holes or things that people are not using, or they feel like they're just measuring and then there's nobody working on it at present.
I can answer something.
I'll just throw it out there that I guess where I see the most potential for growth is the accurate depiction of the architecture of the critical zone beneath the surface, which is often accomplished by digging holes like Perry, or doing the geophysical surveys that we did at Gardner Run and that have been done at Shell Hills and Cole Farm. And I think that depth to bedrock and depth of fractured or weathered zone observations could make their way more realistically into some of the models, especially those that try to depict the movement of water in the subsurface. Discuss. I don't know.
Well, the one addition I would make to that is variation in permeability. You know what I mean? We do actually have a fair amount of work of digging holes, obviously not enough, but you'll never have enough. And then the geophysics, but nobody that I know of, except for Comedy before she left, measured permeability. Yeah, that's probably not right, but it's very limited, the amount of permeability. We've never had people do pump tests except for Comedy.
So I know Chi Chang tried to do something with, so he wanted to do a dye test in the soil to see if there were preferential flow paths. I guess this is kind of talking downstairs, but it was just prohibitively expensive.
So we do have one small study that was done by the Temple group in Shell Hills that did a dye test. And Henry's done some over in mist grouse. Mm-hmm. So the outcomes of both of those are in the literature online, but small scale.
Mm-hmm.
And shallow. It's kind of like
both are shallow. Yes.
Yeah.
But Comedy did a tracer study with lithium, and it was a deeper flow study, and I blocked most tracer studies because I didn't want people putting tracers in the watersheds, so it's totally my fault in some ways. But anyway, we just don't have a lot of data that shows permeability. And when you talk about the architecture, kind of what you're talking about is the permeability structure and the geochemical structure. I mean, I think that's in essence what people are talking about.
So is part of it making the connection between, say, the geophysics and the rock properties, the rock physics models, and how we actually
that's what Jin's working on.
Convert from, say, seismic data to porosity and that sort of thing.
That's what Jin's working on. It's a rock physics model, but even that only takes you to porosity. It doesn't take you to permeability. Yeah. Of course, you can model it, right?
And hopefully some fracture information, saturation, porosity, fracture, distribution.
But the fracture is part of the porosity story, isn't it?
I will try to separate them, at least.
But yes, I mean, the answer is yes, porosity can include fracturing, but how you treat them in the models is a little bit different.
I guess to building on this, is there, and maybe connecting it to models, how do we, what do we envision as a way to test some of these ideas, let's say like in the Reedy et al. 2017 critical zone architecture paper that Sue is on. There's kind of 4 alternative hypotheses for what's setting the subsurface architecture of the critical zone. And we're maybe have a first cut at measuring what that looks like with GPR and geophysics and a couple cores and some soil pits. But is that enough to just keep doing that, or can we get at this by looking at rock physics models or add geochemistry to it? What do we need to actually evaluate some of these hypotheses that are pretty data limited? Do we think we can do that with the current sites, or are they set up for that?
Well, I think on the geophysics side, the more borehole information we could obtain, the better off we'd be. In that all of the geophysical interpretations of the data are relying on having some ground truth information from boreholes. So without that, it's pretty tough. We have a gradational seismic velocity zone. What do we make of that in terms of the chemistry or fracture density or whatever? Without the borehole information to correlate that to, it becomes really tough. So I don't know. I think a couple more strategically placed boreholes in the water, in the different watersheds could make a big difference. In terms of tying together the geophysics with the geochemistry.
Jim, do you want to explain to people what you're doing with downhole logging, the rock physics model, and then how that gets to the geophysics? Like, explain it, like people don't really know what you're doing.
Yeah, sure. Like we did downhole geophysics, mainly using, I think I need the density, like change of density steps.
So they drop a tool down that measures density in some zone around the borehole, density versus depth.
Roughly like 1 meter.
Is that like with gravity or with?
No, the density is by gamma ray.
Got it.
Huh.
It's a radioactive anyway, and another one is the sonic velocity, both P wave and S wave. I think that is the 2 key parameters I need for my rock physics model. Then based on these 2, we have a model to explain how given the chemical composition of the rock, like we know the mineral composition of the rock, then we can predict how the density and P wave and S wave change with porosity and saturation. So it's a function of porosity and saturation, and we can predict what's the P wave and S wave and the density can be. And because we are measuring this, so we can back calculate what's the porosity and saturation should be. Right, that is roughly the picture. Like we can extrapolate the porosity and the saturation from the geophysics measurements.
So how much of this can be done with like the time lapse geophysics, or like can you simplify some of this in terms of the saturation levels with repeat surveys in places where you don't have boreholes?
For the place we don't have boreholes, we can probably use a surface refraction seismic profiles, I guess Andy did, like we did last summer.
Yeah. So you certainly can do more time-lapse geophysics, but time-lapse seismic is tough to do if you're going to do it on a larger scale. We're going to try to do time-lapse resistivity over the next couple months, and we'll see how that goes and what we get out of it. Going back to what Jen said, there's the porosity, the intrinsic porosity of the CIS shale, but then there's also the fracture porosity, right?
Yeah.
And so in the well logs, you also need the optical televiewer to map out the fracture system, right? That's another key.
Yeah.
That's another key log, right?
Optical and acoustic.
And acoustic televiewer, both of them. give you fracture
Acoustic is
locations.
a little bit better because it's sensitive to open fractures.
Right. All right.
But
So
that can only be done below water table acoustic.
good. Right.
Yeah,
But it also gives you the geometry, the orientation of the fractures too. Right?
that's true.
Not just the density, but
Deep.
it gives you some idea of what the fracture.
Yeah, like parallel to the bedding or to some angle.
So one thing in the resistivity that we're seeing already, because Davey Oxheimer's been doing a bit of work out there, part of his PhD, there's a lot of anisotropy in the resistivity data. And it's, so get low resistivities along strike, because of we think the fractures are mainly bedding parallel. So they're along strike and filled with water, so you get low resistivities if you measure resistivity along strike. And if you go perpendicular to strike down dip, then you get higher resistivity. So there is some hope maybe from these time lapse that we can actually learn more about the permeability and how that varies spatially, and because of the anisotropy, might have preferred flow paths along certain directions that can be mapped out. But we have to wait and see what the time lapse.
Is the time lapse, is this like seasonal, like seasonal time lapse, or is this like an individual storm, like tracking an individual storm?
We're going to do, well, the plan is to do a weekly measurement and then to measure right before and after storms events over the next 3 months. So we'll see what we get. But yeah, and there's a lot that can be done with surface geophysical measurements, both extrapolating 3D structure as well as time lapse. But without the ground truthing that comes from boreholes, it becomes pretty challenging to get the level of detail in terms of interpretation out that you guys want in terms of the hydrologic properties and the geochemistry.
Yeah, and even the boreholes, there are some like technical issues.
There's some technical issues, and then there's, I think you're seeing some compositional variability in cesium-W10 compared to cesium-W8. As you get higher in the section near the Kiefer sandstone, you're getting more intercalated limestone carbonate units and some sandstone. And so I think the velocities are higher in cesium-W10, for example, than cesium-W8, deeper in the borehole because of a compositional variability. So I said a few key boreholes were around the watershed. I'm just thinking Shad Hills. I don't know the other ones too well, but where you think there is maybe some geological or geochemical variability, and getting sort of ground truth points here and there, I think and then you can fill in more easily with the geophysics.
So on one hand, with the geophysics or any mapping of the subsurface architecture, there's a question of trying to just get a better snapshot so that we can run our other models on top of that. Right? So this like
an architecture that sits there and it's
exactly.
the way it is.
So something that's imposed that we
Right.
need to go out and measure to include to understand, water ecology, everything else. But then there's the maybe more complicated one of can we actually how much do we try to model the architecture, and how much can we blur our eyes to sort of these variations within the stratigraphy and what is dominated by feedbacks that are kind of critical zone feedbacks versus an imposed boundary condition. I'm not quite sure I know the answer to that, but I think that.
Well, nobody knows the answer, right? So.
But in terms of where to put efforts to think about putting a proposal together, do we try to, are we lumpers or splitters in that sense, or how much does the heterogeneity that we see in the landscape is just like driving everything versus the sort of feedbacks and equilibrium conditions that our models kind of assume, and homogeneous underlying properties can we use that to learn something about, interpret these patterns?
Well, I think when you ask a question so generally, it's like impossible to answer because it depends what specific thing you're interested in. I think there's a lot of homogeneity in shale hills. The outlet is where there's the lack of homogeneity. And I would be willing to believe that that's why the outlet is the way it is. You know what I mean? Like, I think it probably, if you look at the next catchment down, I think it kind of almost wraps around, and then Shale Hills wraps a little bit. It's like they got, they're perpendicular to that hard thing they're trying to cut. And you know more about that than I do, but that's what's going to happen. And that the hard thing is the sandstone and also where the carbonate layers are. And the other thing about those carbonates is some of it is secondary, and that's something that Jin has started pulling apart. I think it's really common that carbonates get dissolved in the upper parts and then get reprecipitated as the water comes back up again and degasses CO2. I think that's probably super common almost everywhere, and he's seeing it. So do you know what I mean? It kind of depends what you're asking. It's still pretty much of a homogeneous watershed, but it got pinned right there because of stuff that you know a lot about, why watersheds line up the way they do. That's what I think.
And I guess I'll put it out there, like Andy said, like I don't know about the other catchments, but like we at Gardner Run can't dig boreholes, first off, like physically impossible.
We have a borehole that we've never been able to get into up on
Joe Hayes.
And we're getting them to clean. We're trying to get a company to come in and clean that up. That's been a long-standing thing.
But still, the story of the heterogeneity in the critical zone architecture at Gardner Run is a different story than that at Shale Hills. It's not bedrock layers. It is the sort of Pleistocene surface processes story. And I'm pretty sure that that's like a difficult thing for the modelers to put into their models. And so like if we like wanted to think about either upscaling or the other watersheds that exist outside of Shale Hills, we are not as far as we are at Shale Hills as to modeling the architecture and how that interacts with water and chemistry at Gardner Run. And I don't know what the status is. I don't know if anybody's modeling Coal Farm.
Yeah,
I don't know, but Perry could probably say
I
that.
don't know either, but there is quite a bit of heterogeneity and lithology at Coal Farm. And I think importantly within mapped formations, and that is like plays an important role in the topography there. And I don't know much about flow paths at Coal Farm, but I presume that it would play a role there as well.
Yeah, we don't have anybody doing a water model for Coal Farm right now. Yuning Shi made a groundwater model for the watershed. It's just kind of like a template almost. It's ready for someone to play with, but we haven't had anybody that's been doing it. And then Lee's trying to figure out, how to make a model for all of Shavers Creek. Like it's unconstrained, so what should we do? How can they start to build it up in a way that makes some reasonable sense? That's where we were just talking with Ying Fan about that.
That's something that I've been thinking about too, is taking the like patterns within each of the subcatchments and looking for patterns within the watershed as a whole. Like for example, the places I showed you where there's like exactly the same geology and structure as at Coal Farm. And I think that you can kind of like make like within Shavers Creek as a whole, kind of group together places that fall into pretty similar categories.
Yeah, I think that maybe that's one thing that could be that could be a way of nuancing or changing the focus of just lithology, but lithology plus structure. So it's not just a matter of whether you have limestones or shales, but it's the order of sandstone versus shale, and whether it's sitting in a syncline or an anticline, that can make a big contrast to what the topographic expression of that is, and then what the flow paths in the subsurface might be sensitive to in terms of the subsurface permeability structure. So that's something that could be tractable in terms of getting building blocks of kind of different units within to help guide. Well, is it enough to just do sandstone, shale, and calcareous shale, or do we need to look at shales that are in a syncline propped up by sandstones and ones that are flat lying, and do they have very different expressions in critical zone architecture?
for these different lithologies, I wonder, do we know enough about the parent, like for example at coal farm, like for different formation, do you really find the parent and what's the composition and how that affects, the chemistry and the soil formation?
I don't know the answer to that question.
Yeah.
Maybe that
Like
is
parent at
something
coal
we-
farm is going to be a tall order because of the lithologic heterogeneity, I think. For similar but different reasons that Garner Run, we don't know what parent is because there's been 300,000 years of like rocks and dust coming.
Yeah.
So that's like an also terrible question. Hard.
I think you're being too negative. I mean, down in the valley floor, around that's pretty hard because it's all together. But up on the ridges, we're starting to have a model. You know what the parent was, but we also know there was dust input. We know that it seems to have collected some from the ship. You know what I mean? We are getting a model of how it formed. So I don't think it's quite as bad as you're making it sound. We do have models of regolith formation. Da Cheng is running a model of regolith formation. He never talks about it because he's gotten hung up on the water side of it, chapter by chapter as they go through. But we do have models of regolith formation, and his model was meant to be able to predict how porosity grows in the rock as weathering happens, and then also predict how permeability changes. So we have models like that, and we could run those for the other systems. We never got as far on that as we wanted. And we have soil gas and water chemistry versus depth in the soils in a lot of the places. That's all teed up for a model, and we just haven't had the bandwidth of people time to do it. But, there are modeling issues to that, like there are reasons why to make the model is hard. But I think if we had people, we could do it, and it's just, we just don't have the people time. We haven't had the people time to do it. The paper that Liz Hasselmuller did where she looked at the shale pits and she measured every root in there that she could see, and there's microbial CO2 production data in there. I mean, there's like all this data. It is ready. It is so ripe for a modeler to model that. We just haven't had the bandwidth to do it.
But do you really think what the model can tell us? Like, you have this data and we can model the process, but can we learn something new, or what's the purpose?
What do you think?
Sometimes I just feel like it's a hard. I am not a modeler, but
it's hard to run the model or to
No,
learn something from the model.
Learn something.
Yeah.
Like,
Well,
is the
maybe-
model too specific or something, you mean?
Not too specific. It's like you can get the results kind of match your measurements, but what I can learn from the model.
So I think that's a really good point, but there are different ways to run a model, right? I mean, if you're modeling it just to simulate it, you're kind of being an engineer, right? You're making a model to simulate things, right? If you're modeling it to learn how it works, you know what I mean? You're trying to build models into your paper that you're writing right now because you're trying to make sure you really understand how the thing works. Because you can make all these observations, right, that tell you a lot, but until you synthesize them into something, and that something's called a model. And the more complicated it is, the more it has to be a numerical model, right?
So it's the science question, I guess.
Right.
Well, I mean, the other way I think of it is if you have, if there's some contrast in observations that you think you want to test whether or not the process that you think is driving it is actually responsible, or if it's possible to, for example, at the Shale Hills, can we reproduce the asymmetry in topography just with a climate, microclimate model? And that's something where, you kind of need to have a model to test your intuition, to quantify your intuition about how the temperature fluctuations might drive downslope regolith transport. And so if we have observations of the critical zone architecture of spatial variability in the critical zone architecture, that we could say, can we get this from just compositional variations, or do we need to explain this with something that feeds back into the ecology. And so, but having those observations and like kind of laying those out as the justification for the model, I think is useful. And so if we have observations already that we can kind of list or inventory, what are the confusing, the interesting and confusing contrasts that we can't easily explain, and that can be a guide for moving forward with modeling or figuring out what processes we need to, we're missing in our conceptual models.
So I'm gonna go downstairs just to flip back and forth. You're kind of halfway through your time. I think the next seminar we might actually have a report back. So this group would report back, the answers to these questions, theoretical answers. So are you getting, you might think about whether you're getting there to the answers to these questions.
I can just say a few more things from the geophysics perspective here. I mean, we can do geophysics and sort of characterize a subsurface where different boundaries are and so forth. And that's one level of imaging that can be helpful, I guess, to answer your questions. But one thing I struggle with doing geophysics in the critical zone is really understanding from a geophysical perspective how the geophysical measurements can be used to address critical zone science questions, other than just characterizing. Okay, here's the water table, here's where we transition from regolith to unweathered bedrock. Now, this is how thick we think the soil is here versus over here. We can certainly do that kind of characterization, but beyond that, what is the geophysics useful for? Are there process-oriented questions that you could actually get at with geophysical observations? And that's where I keep coming up with blanks.
Yeah.
Other than some of the time lapse.
The time lapse and sort of
works or helps.
Enabling you to make spatially explicit observations rather than just point measurements. I think you can set up questions that you can test, but the only way to test them is with geophysics, I think. And in that sense, that will help you.
Well, at least from an ecological perspective, I'm really interested in how the local environment affects how plants are growing and how plants are producing and things like that. And so I feel like what you're saying, these different, geophysical characteristics, that could have a huge impact on what a plant is going to be producing in the soil there. If there's a lot of bedrock that has phosphorus, are the roots that are right near that area going to produce a lot of phosphatases in the soil to get at that phosphorus? Or is it just or do plants just kind of spread it out everywhere? So I think having things like that would really help from an ecological perspective.
Yeah, I don't know. The critical zone geophysics seminar was really helpful, I guess, last year at this point. And I too struggled with that question coming from someone who thinks on timescales that are much longer than the observations that one would make with time-lapse geophysical surveys. But one thing that I was thinking was, for example, if let's say we had a functioning regolith model, right? Or regolith production model, right? There are going to be water, chemical, and sediment fluxes that come from that model that could be checked against observations made from time-lapse geophysical surveys. And that's sort of how I imagine bridging critical zone questions. So for example, over time development of regolith with what we can write, because today's geophysics are just a snapshot of the modern. And so a success or a way to answer a question would be, is our model accurately representing things like, the movement of water at, the rate and depth at which it occurs in the subsurface? And does that, the representation in a regolith model match what we see from time-lapse ERT, for example?
So I guess, another way, so if you extend this to just beyond critical zone science, but do you have an example of where geophysics is fundamental to, beyond, I guess I'm trying to separate out, it seems like the characterization oftentimes leads to the questions that emerge from that, or do you have like an ideal example of where that works?
Well, I mean, we do a lot of large-scale Earth imaging, mantle imaging. I usually start with a science question and then try to figure out whether I can come up with some geophysical observations that will let me address that process or or problem. So for me, I guess I don't know enough about critical zone science to say, okay, I could take that approach with geophysics other than going out and mapping.
Yeah.
Like I don't go out and do surveys of the 410 or 660 kilometer discontinuity globally just because I want to see where they are. I have some idea. Well,
Really?
okay, here there might be a plume, and so the 660 might be perturbed, and
Yeah.
so I want to go focus in this area, to see whether there's evidence for that perturbation or not. And I guess applying that to critical zone science, I don't know enough about the science questions to say, okay, here's the science question, and if I make the following geophysical observations and come up with the following geophysical model, I'll be able to address that question.
I think, yeah. So from my perspective, the parallel would be thinking like specific, regolith production models might make predictions about what the pattern of soil thickness on the landscape is and how that varies with the surface curvature. And you could either calibrate those models with a bunch of point measurements of soil depth by going out with an auger or digging pits everywhere.
Yeah.
Or if you have some way to get a proxy for that from geophysics, it allows you to test that model more spatially distributed than just with point measurements. So that's sort of one sort of easy connection to existing models. The other one is the sort of thickness of the weathered bedrock zone. And that, I think the challenge is like we're starting to have some models of what might govern that, but like we're so data limited that we don't even know where to start or like what questions to ask about what controls that variation. What's the dynamic range in these landscapes? Is it systematic, like all the shale landscapes have one pattern and all the sandstone landscapes have a different pattern?
Yeah.
Does it depend on whether you're, like how steep the topography is or
Climate.
what's that?
Maybe climate.
Maybe the climate, right? And so I think that those sorts of questions, there's maybe, we have few enough observations that are connected to other measurement, to some conceptual framework that just having even one snapshot is helpful for kind of helping to develop those hypotheses.
Yeah, to me, I think if you can successfully apply this geophysics tool to characterize the near subsurface, is a huge success. I think it's not only for CZO stuff, it's also for some, for example, geohazard assessment, like landslide, that you can kind of estimate how thick the loose materials can be, right? Something like that. I think because just from applied science perspective, you can prove this method works for near subsurface.
But I think the challenge is the ground truthing and sort of how, like, it's one thing to just sort of have a sort of fuzzy image that you can maybe draw some lines on or like make a guess, but to have like, this is what confidence we know that this is the boundary between these two properties that we can plug into our models. And to me, that if we had that's what then becomes really important. Those become really important constraints for models of critical zone evolution. And so whatever we can do to kind of help clarify like what for a given setting, how do we do things like map soil thicknesses or something that we can use to be confident about what the interface between soil and rock is, or what does unweathered bedrock look like, and does that, how variable is that, and can we get at it with just like one borehole and then extrapolate to a whole catchment? So I mean,
Right.
to me, that's like there's a huge gap in terms of.
Yeah. Well, yeah. I mean, hopefully, that was sort of what drove our DOE proposal. Those kinds of questions, and hopefully, we'll get there once we get our 3D seismic model together. Already, we're seeing what they're trying to get a handle on what some of the resolution issues are. And the images we've developed so far, the 2D images from what we've done, you can see the soil layer pretty clearly at really low velocity. And then you get this gradient zone where velocities increase, and then at some depth you get to where the velocities stop increasing. And how resolve that gradient is a hard problem. That's what we're working on right now. And that goes, with your weathered bedrock, but not really soil, kind of, that transitional layer, and how thick that is, and how does that thickness vary. So I think those things we can get at. It's a lot more detailed geophysics.
Yeah, I'm quite positive about.
Well, linking that to some conceptual model, I think would really help. Why do we want to know this? If it's 5 meters here and 10 meters over here, how is that going to help us?
Yeah, and I think there's this paper, this review paper that Sue and Cliff put together 2 years ago now, to me does a nice job of sort of summarizing these like emerging competing hypotheses for what's driving the patterns in the subsurface architecture. And the questions are whether or not you can actually can you get data that actually is enough to distinguish between climate versus tectonic stress versus hydrologic controls on subsurface weather, and especially if they're all feeding back with each other and interfingered. Okay, so
borehole every 5 meters down the coast.
or we could just remove just stepwise remove the entire landscape with a big excavator.
Nice.
Okay, so we've sort of gone down that path of additional measurements. Could be geophysics that is constrained by ground truthing through boreholes observations. It's maybe one additional measurement, one type of additional measurement, or two types of additional measurements that we should be making. What else beyond that in terms of measurements to help us resolve some of these questions about what's driving soil development and landscape evolution? Do we need?
Like Sue said, like porosity and permeability. Like I just know it is difficult to measure at Garner Run with instruments that are traditionally used, like ring infiltrometers. So it's possible that geophysics can, we're starting to get there where geophysics can help tell us about hydrologic parameters in the material in the critical zone.
So what about the hydrology itself? Right now we have the well data, and we have the soil moisture profiles in the groundhog pits, and then the Cosmos soil moisture, kind of a larger footprint. Is that enough, or is that capturing the types of patterns in soil moisture that are important for constraining our models? Does it matter? Do we, for the longer time scale processes, does monitoring any of that make a difference?
At Coal Farm, for instance, it's a fundamentally different landscape than it has been over long time scales. So I don't think that data necessarily helps with long-term landscape evolution, but could be useful for different questions.
Maybe it's a way of investigating the architecture a bit more by looking at how the landscape responds to storm. The hydrologic data is important for constraining the architecture properties, or is another data point, or at least trying to distinguish between hydrologic or structural controls for the patterns in geophysics.
Yeah, time-lapse geophysics, you would track hydrologic flow that then tells you something about the architecture. So you could have a model of the architecture, you know, not necessarily monitoring a process, but have a model of the architecture and then track something like a storm and see how that time difference data interacts with what we think of as the existing critical zone architecture, like a hypothesis test. You know, we think that we've imaged the architecture and we think it has this porosity structure. When it rains, does the water, as told by ERT or whatever, follow the velocity that we think it does or something?
Since inception, the soil moisture data sets have been the most requested amongst the team and from outside collaborators, hands down.
Mhm.
And I think the fact that there's a wetting and drying curve that happens on different temporal scales is incredibly important, whether it's storm related or it's just seasonal variation.
Yeah, I mean, it's huge for root turnover and for distribution.
Yeah, I mean, I think for the short time scale, it's like everything, or not everything, but it's clear that those measurements are like the fundamental observations for thinking about how a landscape responds to storms and seasonal variations. And then I guess if we're sort of breaking this out into thinking over longer term in questions that are related to, you know, critical zone evolution over longer timescales than we can monitor, you know, it maybe becomes another tool for investigating the architecture. So can maybe lump everything together into like characterizing the current snapshot of the critical zone architecture as something that's needed, and that entails geophysics, soil pits, borehole observations, and this is just one way of characterizing the state of the landscape and the subsurface.
Well, if you're going to do boreholes, then getting pump tests and whatnot out of the boreholes, so you get plain estimates of hydrologic properties. Boreholes, I think, would be really, really critical, and that'd be another reason for doing the boreholes, not just to get the geophysical data, but you could. Can you date the water at all?
Yeah, that's a good question. Yeah, I don't know if people are working on that question right now in the CZO.
So they did in the first funding cycle. Chris Duffy's group was looking at the age of water, and they were measuring the deuterium and the oxygen isotopes from the rainfall up by the Met station. That aught's been gone. That was Beth Boyer's equipment.
Yeah.
And of course, in the pour water and then at the weir to get at it, resident time on average is around 9 months in Shell Hills.
Yeah, but like maybe like the depth measurements of water age, right? Like that would be a cool complement to
Henry has that data for Shell Hills.
the like architecture map. Then we have some sort of time varying pattern in the geophysics, and then it would be cool to then also pull out the water in maybe shallow and deep points in the landscape.
I think it's in Pam.
In Pam Sullivan's paper. Okay.
And Katie Gaines, you know, had stuff
Okay.
for that.
I mean, that'd be cool. That'd be cool to do it in a place other than Shale Hills, maybe.
It would really useful at Coal Farm too, because it would help a lot with me looking at contaminants and determining the source and when it was actually put into the groundwater.
Yeah, I mean, I'm sure that flow paths at Shale Hills are not the same flow paths as at Garner Run and at Coal Farm.
So is there actually a 3D physical hydrologic model for these watersheds or not? It's like a mod flow model, you know?
Not for
Yeah,
the
Where you put in the
as I
topography
know.
and everything.
It's all through PIM.
PIM is kind of focusing on the shallower subsurface, like they treat like below 1 meter is all bedrock.
At Garner Run, bedrock depth is 1.8 meters in the PIM model, everywhere.
Okay, so
Yeah.
in terms of what's needed, I guess, is a more
But
realistic.
we don't have a hydrologist that has a
physical hydrology
to
model.
do that.
Yeah.
Maybe we should hire Sorry.
Yeah, so I mean, but this is like, I think, so there's this side of this that is, you know, from a longer term perspective, putting in some geologic context for what the architecture looks like as a template for shorter timescale processes.
Yeah.
And then there's the sort of science questions that are the longer term coevolution of the critical zone in the landscape over geologic timescales. And so what other measurement, you know, so those are maybe less about kind of monitoring measurements that we need to be taking sort of, you know, have something that's telemetering data so that we can see it in real time, and more like sampling campaigns either through geophysical or borehole or geochemistry sampling. You know, so the second half of this maybe is like, what types of tracers or measurements do we need to constrain our longer term models? Are we making those measurements? And
I think one measurement can be is like we can identify some hotspot for example, geochemistry, or maybe also for ecologic, like the area with higher variation for redox boundary, for example, close to the stream beds. Like the cycling, you can see like they changed a lot seasonally compared to probably ridge is always dry, for example. So if you can identify some hotspot, like making more measurements on that can be interesting, I think, to show the temporary change.
Does that inform like are those hotspots going to change with time though?
Yeah, I think it's kind of like when the water gets high, it becomes more redox. When it's low, it gets oxidized. So you can, like near the stream beds, you can see that pretty frequently.
Okay, I was in terms of the long-term evolution of the critical zone. That was my question, is like, can we make geochemical measurements and extrapolate for the long term?
This is probably more for the short term, but people, they care about this.
Right, yeah, for sure. I'm just thinking of the like.
Well, there's also the other thing that we might be able to get from this is, like, there are long-term signatures of the chemistry that are encoded in the soils and in weathering profiles on the hill slopes. And then we have the shorter time scale fluxes that we see in the solute fluxes. And that the mismatch there could be telling us either something about process, but also if there are, perturbations to the system, we might be able to pick those up in the measurements that we're making today, like solute flux measurements or hill slope, subsurface flow water measurements, and compare those to, like, if you extrapolated this over geologic time, does this require like an acceleration in weathering that's due to human impact or climate change or something like that? So there might be ways to kind of use to ask questions about long-term equilibrium and disequilibrium by probing the system, probing the same underlying process, but like at different points within the system. So the rock and the water that's interacting with.
Yeah, that sounds interesting. Yeah.
What's our time for this?
1:30 is when we're done. Did she want us to go back downstairs or just break here and call it good?
It sounds like we're going to summarize the next time we meet.
So here and then we're done.
That was my guess. So we can.
I'm going to have to say early then I got it.
So I guess, yeah, so maybe we haven't really, we haven't really gotten to the second question here about what additions to our modeling tools are needed and what additional processes are important to add to existing modeling tools. So is there anything that...
Read the question again.
The question is, what additions to our modeling tools are needed and what additional processes are important to add to our existing modeling tools?
No, our modelers are downstairs.
Yeah,
Yeah.
I was gonna say I
I
don't
mean,
know what.
Like all
I mean,
of them.
I don't know what we're
accurate-
using.
Yeah,
Yeah.
accurate representation of critical zone architecture in hydrology models.
Okay, so I can address that real quick. When Yuning was a student, this was an ongoing conversation that we had as we were all getting to learn PEM. And the questions really were with all of his, and Ting has the same group of, 25 parameters, what's important and what's not. How do you can't measure everything.
Oh, no,
Well,
I'm
that's
just saying
important.
like depth bedrock,
That is important, I think, but maybe
Make it-
is it?
make it accurate.
What's better?
Oh, see.
I mean, it's definitely 10 meters below the surface in the valley fill.
Actually,
In the valley
the
floor.
real problem is.
Actually, it's deeper, I find.
Yeah, I'm sure, yeah, I think, or
It's
is it
like
much
20
deeper?
meters.
The
20?
real problem
Okay.
is the models we're running don't have groundwater in them at all. That's the
We were
real
just
problem.
talking about that.
That's the real problem.
The models have any trees or root data, anything like that?
The models have trees, yeah, they're talking about that downstairs. They have like the average tree, has root uptake and everything.
So I guess, maybe another way to get at these questions is how do we bridge the gap between field and modeling more at the. And do you have ideas that you would like to implement in models but don't know where to start, or feel like there are things missing from that the modelers are working on that you could inform, or I guess
I once again, I'll use Gardner Run as an example because I worked there, and I know that Da Chang used my boulder map in his model at Gardner Run and showed that like sometimes for some things it mattered, some things it didn't. But one way would be that hydrologic models enforcing their flow through a landscape can, to a first order, tell us what the porosity and permeability of the regolith is, right? It's either like really high or really low. And from my surface mapping, I can't tell what the architecture below the ground is until we like did geophysics. But a hydrologic model that routes flow, at varying speeds through a subsurface of varying textures might be able to say, oh, we know from this model that it can't be solid rock, solid impermeable rock 2 meters below the surface. But it also can't be, super permeable 10 meters below the surface. It's, somewhere in between. It might be able to a first order constrain what is under the ground. If you like pour water on a landscape and it either comes out really fast or comes out really slow, and then you match that with reality. Does that make sense?
I think one of the challenges that we came out of that was that if the only measurements of, say, that we're calibrating the hydrologic models come from the 4, points on the groundhog pits plus the outlet, the degree to which you can kind of resolve finer scale details is limited by the observations that you have. Or you can sort of treat things as a bulk contrast between, say, Garner Run and Shale Hills, but trying to figure out like, well, what permeability structure does the one surface type versus another, unless you have sort of a integrated sampling campaign to go out and test that question. I think it becomes like there's a iteration that has to happen if we want to, like, if we identify problems or identify questions that are interesting that we can test with a model, but then require more field data to help constrain. So
I think it kind of gets to Jin's question before I left, which was like, okay, so you can make a model and put all the numerical stuff in it and put all these and then you can get it to fit by changing, you know what I mean? But then what do you have, It's sort of like we have to think about why are we making the measurements and what is the model that we're learning and what are we trying to do with it? Because we're never going to have enough data to parameterize everything. And even when we do, we're going to have a model that we don't even believe in.
It comes back to your conceptual models for actually what's happening.
Yeah.
The different hypotheses that are articulated within the context of those models. You mentioned you have somebody doing a regolith model. Is that like a 1D thing, weathering thing, or is it like a?
It is 2D, I think.
2D, but they're putting in heterogeneity? Is it all sort of uniform? Are you putting in?
Well, the way we were running it was, he's a student of Lee's, is we were starting with exposed shale and allowing weathering to grow the porosity, you know, and the change the geochemical reaction fronts, you know. So it's kind of like growing heterogeneity into it. But no, he was going to put, he had all these plans. He was going to put fractures in and this, that, and the other. But, you know, he's been here 4 years and he hasn't finished it. So we don't typically have heterogeneity. I mean, I do a lot of modeling with Marina Lobdova, who's like right over there. We've never tried to model shale hills. You know, we do these thought experiment models, and we have done thought experiment models with and without fractures. You know, we could do that for shale. We could do it for shale. We could do this. We just have never done it. Like all this stuff is possible. The question is, what do you want to do? What's the thing that's going to move you forward? We could make a numerical model for shale hills. We know a lot about it. We could put everything in the kitchen sink in there. We could make it fit, you know. Is that really what we want to do? That's Jen's question. Because then what do you have? Well, you have a simulation of reality, you know. So we tend to do more sort of thought experiment models.
What comes to end, I think identifying what like the key contrasts are that we see in our watershed. So for example, can we describe like can we explain like the difference in regolith formation on shale hills versus Garner Run just by changing the fractures, right? By having wider spaced fractures? Or do you need to also incorporate the geochemical characters that, you know, the rock chemistry differences as well? And do you also need to include how dependent is it on the regolith thickness or the types of trees? And so we can start with like these big contrasts that we can observe and are sort of easy to motivate like what we're trying to understand, and then use the models as a way to kind of help figure out what matters or what doesn't. And I think for the longer term stuff, there's lots of great opportunities within Shavers Creek of examples of things that are operating really differently depending on what the land use or you know, microclimate or lithology or structure. So there are, I think, opportunities to test out some of those kind of first order questions. It's just a matter of sort of framing them and then having the observations to set up the modeling exercise.
It's good. I gotta run.
Did you answer the question so that we can report back next time?
You want boreholes every 5 meters.
But then your watershed is different. It doesn't operate the way it used to operate. Right? It's the Heisenberg uncertainty.
Well, I want boreholes every meter. And
Is there
Ron
an
wants to bring
easy
in a
way?
caterpillar and
None of
move the hill slope.
Destructive
The Heisenberg
that you
uncertainty,
could
as soon as you know
measure
enough
depth
about
to
your watershed,
that
and it doesn't operate the way
say
it
what?
used to.
Landscape
GTR.
and static
Andy.
something.
Yeah, you guys.
GTR just
Well,
strictly
and that's what
GTR
I've been trying
And
to
that's
do
what
with
we're
augering.
Yeah.
To like
to some extent.
Yeah.
See, because okay.
You can do it at Coal Farm much more easily than you can.
Because it's fairly
Coal
difficult when they were
Yeah.
trying, when
Yeah.
Nikki was trying to do it at Shell Hills. And I imagine Garner Run would be.
Garner Run would be
It would be
Right.
impossible.
And
So,
yeah, that's what I've been trying to do at Coal Farm. It's time consuming. And their point measurements.
yes, right. It's an investment.
Yeah.
But
It's probably still better than GPR though, because there's so much clay.
Yeah.
I don't know that
Coal
that's true. I
I
think
thought
that,
they tried GPR. And they
Yeah,
had a lot of
Sometimes it
trouble.
works, sometimes it doesn't.
but I think we've looked back at that like that data, and I think there's more there than we thought
Oh, really?
originally. And I have interest in trying in the perpendicular direction to that original line, because I think that you would see more and that it would be more helpful.
That'd be awesome.
Is it because last year was wet?
This was before I got here that the GPR was collected. Was it that spring before? So spring of 2017? Spring of 2017?
Yeah, spring 2017 sounds
Yeah, but yeah, I would like to get I need to talk to Greg about coming back to, and he said he would. We just have to organize the time to. I don't know if we'll do GPR or ERT at Cole Farm in the direction perpendicular to the groundhog train set that we've
You want to go
collected.
across both?
Yeah.
Both.
And yeah.
So one conversation they were having downstairs was they use BioBGC to model, you know, the sort of to couple to the land surface and then what does it predict and this, that, and the other. And they were trying to figure out when it wouldn't work. And as long as they could tweak their knobs to change the water from one setting to another, then it was going to work, you know, because water was in there really well. So then I said, well, what about the shale barrens, this thing that I've been asking you about by email?
Yeah.
Because forests on shale, like Shale Hills, are very rich forests, but forests on shale barrens are very poor forests. And yet the underlying lithology is the same. So it would go into there's no shale in BioBGC, but what's in there is the texture, I guess, and the soil depth. And that seems to be the difference between those two.
Yeah.
And my guess is that it's the erosion rate is different for the two. That's why I was asking that, but I don't know. But anyway, I don't know. I thought it was sort of interesting to ask yourselves, like, where does your thinking fail?
Areas
That's in essence
where
what they're
there's
asking.
just,
When does their
it's just
thinking
dirt, there's
fail?
no trees.
So what does that tell you about
But where?
what you haven't understood yet?
But where though?
They're
I
just
think it's
random
over near
places.
Philadelphia.
Oh God. Okay, what? Sorry. Where are the shale barrens?
They're around Pennsylvania. They're just like,
They're just,
they're often conserved by conservancies because they have these really rare plants in them, because sort of the kind of forests that we see normally don't thrive.
Okay.
I don't know. It's like, where does your thinking fail? It's
Yeah.
kind of an interesting way to move forward.
yeah, I mean,
Because we tend to think, how can we build a model that's going to make a better and better model, you know? But you can also think, where are you going to fail?
so like ever since you mentioned shale barrens to me, I've been thinking about them, and like one of the things that I wanted to mention was like, can we get like geophysical and geochemical properties of these shale barrens so we can figure out what makes them different and why are, you know, the normal trees that seem to be able to adapt to their environment really well, whether it's shale or sandstone, you know, they do their roots differently. I just, you know, that was my paper. But then why are they failing on these barrens?
Where's the
Where
nearest?
do they
Where's the
happen?
nearest
There's-
shale barren?
Like,
Is it in
Rothrock?
Rothrock?
There's not far away.
Are they in Rothrock?
I don't know, but it's not too far away.
Yeah.
What were you saying, Mary?
I was just gonna ask, like, are there like structural or topographic differences in those places versus where we see shale with?
Kristen was saying they're often sort of on hills that are like right at the bottom of the hill is a river. That's why I was thinking the erosion rate was faster, you know? But I guess my point was not necessarily to derail and everybody talk about shale barrens, but it was like, ask the question, where does your thinking seem to predict the wrong thing? It's interesting.
Yeah, I mean, I think one thing that has come out from this Garner Run geophysics work is the idea that the weather, you know, our interpretation of weathered bedrock is thickest underneath the valley floor in Garner Run, and that's opposite of Shale Hills, and it's opposite of most.
It's thickest in the valley in Shale Hills. It's like, you're talking about the augerable soil?
No, the weathered bedrock, the depth to intact bedrock.
So down to the pyrite oxidation
Yeah.
front? Okay. Because I'm not sure you know where the oxidation front is in Garner Run, if it's there at all.
We know.
No, but I think if you look at if you assume that the P wave velocities are some indication of depth of weathered or fractured bedrock, that you can, if you look at that pattern, it pinches out on the hillsides, and then gets that zone kind of between like 2 and 5 kilometers per second is thickest underneath the valley floor in Garner Run. And most other places, it's thinnest where in the valley floor. So that's sort of maybe, you know, a contrast to what you might expect in terms of your models for like how the weathering zones on the hill slopes are connected to channels, and whether this is something that's distinct about Garner Run, that you're in a net accumulation zone, or something that's, that's related to how close you are to some steady state might be different between Garner Run and Shale Hills or other landscapes, where I'm thinking of like the St. Clair paper. I think all of those weathered zones pinched out underneath the channels, and a lot of these models show the kind of depth to intact bedrock is shallowest in the valley floors.
Well, can I get to the board? I feel like the need for a board. Like, I don't know, like a Garner Run.
How deep is that? I think it's
50 meters.
What's 50 meters?
the weather zone.
That's our interpretation.
Oh,
Yeah.
This is Garner Run.
Yep.
So the water table, where's the water table? Okay, it's like 200 feet down or so. It's pretty down. It's far down, right? Is it above here? It's gotta be above there, but is it much above there?
5 feet in the valley floor, right?
The water table?
No. Think how high above the valley
Oh.
bottom.
Oh,
of the
I don't
hillside.
know.
But yeah,
But I
that
think
looks
what
reasonable.
What you're saying is that what you see by GPR or something thickens down here, right?
Yeah.
That's what you're saying.
Correct.
What I'm saying is, I'm not sure it could be weathered all the way down that far,
Mhm.
which is exactly the way it is at Shale Hills.
Mhm.
You know what I mean?
Yeah, I mean, we have our GPR that tells us that depth to unfractured Tuscarora seems to be on the order of 10 to 15 meters on the ridge lines.
But if we just stick with the seismic, even on our survey at Joe Hayes Vista, it's only like 10 meters before you're getting 5 kilometers a second in P wave velocity. And so
I could be completely wrong. I think it's probably something has changed in that rock down to the water table,
Yeah.
which you can't see with geophysics. Partly because it's 99% quartz. Do you know what I mean?
Yep.
So it all comes down to defining everything. You know what I mean?
But I guess that would be something where my preconceived conceptual model of what I would expect the geophysics to look like, or is broken there. In terms of, I don't have a good explanation for what would be driving that contrast, or why that would be so.
Is it because it can't get out of the valley, like what she wrote in her paper? It's coming down into the valley pretty easily, but it's not going out of the valley easily.
Yes, that's sort of the working hypothesis for the valley floor. But this contrast between the water table and what we're interpreting as, unweathered.
Why is the water table where it is?
Yeah.
Well, I think that is a really good question. I mean, that's something like we keep asking Jen, does the weathering dictate where the water table is, or does the water table dictate where the weathering is?
I mean,
depending on the day of the week, he answers it differently.
Because it could be that the unweathered sandstone is still pretty porous, right? Or I mean, is
the weather of the sandstone is porous?
I don't know. Is
No,
is unweathered Tuscarora formation still pretty porous?
No, it's very low. Like
The porosity is very low.
less than 5%.
Porosity.
Yeah, porosity.
That's the nanoporosity, though. Right?
I checked. I think it's low.
The
Are you including fractures?
I was gonna say,
or you're only
I'm
talking about
I'm not
thin section
talking-
porosity?
outcrops of the
So the
Tuscarora are
water
always
table
very
is
heavily
going to be
fractured.
not just a function
Yeah,
of
sure.
thin
But
section
I'm
porosity,
talking
it's
about
also the fracture porosity.
Yeah, I'm talking about the small scale porosity.
Outcrops of the
But
Tuscarora are
where the
extensively
water
fractured.
table is, I think is a really big question that I don't know. I don't know. Like, that'd be a great paper, what controls where the water table is, because it's like such a basic thing. I don't think anybody understands.
But there's a climate story in there. That's just me.
Well, do you feel like this is a good conversation? Did you get somewhere?
I think this is helpful.
Big questions.
All right. Well, thanks, everybody. I will take my notes and compile them into something for the next time we meet.
Did you record now?
So, John,
Well, we're
Yes.
gonna find out when it's compiled.
what's the deepest?
Thank you so much, Jeff.